Virginia Smith has joined us online. She tried very hard to be here in person to give her viewpoint on privacy and federated learning. She really has been one of the leaders since the beginning. She is the Leonardo Assistant Professor of Machine Learning in Carnegie Mellon. Her research spans machine learning, optimization, distributed systems, and she's obviously won a number of awards for the many seminal pieces of work that she's done. Most recently, I noticed that she won the Samsung AI Researcher of the Year Award, if I'm not mistaken. So that's a wonderful credit to both her and her students, I'm sure. Virginia, can you hear us fine?
Yes, yeah, can you hear me? Okay.
Great. I'm sorry that we don't have a camera so you can see everyone here and online. Yeah, over to you. Thank you so much for being here to join us.
Perfect. Thank you so much for having me. And yes, I really wish I could have made it there in person, but I really appreciate the opportunity to still speak with you all virtually. So yeah, as was mentioned, a lot of my research, especially over the last several years, has been in the space of federated learning. And today I'd like to talk about two critical concerns in the federated learning space, one being privacy and the other being accuracy, and accuracy specifically through the form of personalization, which is really crucial when you're thinking about accuracy in heterogeneous networks like practical federated learning systems. So before I get to that, I know everyone is quite familiar with the space of federated learning, but I wanted to start this talk off with a very brief motivation. And I want to do this partially because I have, a lot of people come to me and say, where is federated learning going? Is this still an important problem? Do people still care about the, applications of federated learning? And I think there's an obvious answer here for why federated learning is important and will continue to be increasingly important moving forward. And that's very simply, if you think about existing and future applications of machine learning, you might be thinking about things like language models or machine learning for healthcare or smart homes or smart cities. These applications all rely on data, and they rely on lots of good data, right? This is something that we've seen over and over again, that data is a really critical differentiating factor in these applications. And more frequently, to get access to all of this data, we have to go beyond the data of a single user or a single hospital or a single sensor, right? We have to gather data from multiple sources and across multiple organizations and from entire networks of sensors, right? And this is where federated learning can be incredibly useful. It can help you to process and gather and obtain knowledge from this data more efficiently, more effectively, and in a way that improves privacy and security. So in thinking about some of these, key concerns in federated settings, at its heart, you're trying to solve some distributed learning problem, right? You have a network of clients, distributed clients, and you're trying to train some model over these clients. But there are a number of things that make this really unique and present new challenges beyond existing work in distributed learning. So if you think about cross-device FL, like was just mentioned, there can be major concerns here around efficiency, especially the cost of communication. You might be learning over massive, slow, or unreliable networks. Privacy is a major concern. This is one of the motivations to perform federated learning in the first place, but we're still sending information over the network. There are still ways that sensitive information might be leaked. So it's really critical to think about how you can still ensure privacy throughout this process. And then finally, another key way that federated learning differs from something like standard distributed learning, say in a data center setting, is that because the data is being generated and gathered on these edge clients, the data might be very different from one client to another, right? You might have unbalanced or non-identically distributed. You might have heterogeneous data. And this heterogeneity can show up not just in terms of the data, but also in terms of the underlying devices or clients and their computational capabilities as well. So this, these broad challenges, these are things that I have been spending a lot of time thinking about over the last several years. My group and I at Carnegie Mellon have been developing foundational tools for the field of federated learning. We've been, developing techniques for efficient distributed learning, focusing a lot on this issue of heterogeneity of data and systems, and also more broadly developing solutions for trustworthy machine learning. including things like privacy and robustness and fairness, and thinking specifically about their application to federated learning. A major part of this has been partnering with folks who are deploying federated learning in practice. So we've developed solutions that have been deployed at places like Google and Apple and Meta. We've worked with partners at Semantic. We recently proposed a solution that was a winning solution to this Privacy Enhancing Technologies Prize Challenge, which was looking at privacy-preserving cross-silo pandemic forecasting. So I'll talk a little bit more about that later in the talk. And we have really, been from the get-go quite interested in developing tools that are reproducible and open source. So, I think Flower is a big part of this, and we've also developed some of our own, tools here, things like the Leaf benchmark for federated learning. And I have also been helping to run this Flow seminar, which is a weekly worldwide seminar which covers topics in the space of federated learning. So this is open to the public. It takes place over Zoom once a week. And if you're interested in this space, I would definitely encourage you to check out that seminar. All right, so that was a brief overview and motivation. Today, I want to talk to you about two concerns specifically. I want to talk about this issue of privacy and this issue of heterogeneity. So I wanted to talk about, how we can reason about these concerns and also how we might be able to tackle them, and specifically what sort of tensions arise between these two challenges of privacy and heterogeneity. I'm going to talk about this in two contexts. I'm going to focus first on thinking about privacy and heterogeneity in cross-device federated learning. And then I'm going to talk about some solutions in cross-silo federated learning and how they differ a little bit from what we developed in the cross-device space. And in the second one, I'll touch on some of the techniques here that we used as part of a winning solution to this cross-silo pandemic forecasting challenge. All right, so starting off thinking about heterogeneity broadly, this really boils down to, I think, there's a lot of ways you can think about the issue of heterogeneity, but one of the key concerns that this brings up is if you know that the data differs from one client to another in a federated network, how should you incorporate this information in terms of your model? How should you be modeling federated data? And there's a couple natural extremes to consider. You could learn completely local models, one model for every client in the network. This is, super personalized, but you're not learning information from clients that might be related to one another, right? This is the whole promise of federated learning, that people might have data that might be useful for, other clients in the network. And so the other extreme, is to learn just a single model across all of the clients in the network. And the clear downside here is that there might be, a limited capacity to then learn the unique personalized behavior on each of the clients. So ideally, we might want something in between these two extremes. If we know that data might differ in various ways from one client to another, which is very common in federated settings, we might want to be able to learn between relevant related clients in the network while still sharing information, but developing models that are personalized to the unique behavior on those clients. And this is something that we propose right sort of from the get-go in terms of thinking about the problem of federated learning. This is one of the key insights we had many years ago now at this point, which is this can be naturally addressed by developing solutions for personalized federated learning. And specifically, a key tool here, which has become very common, is to think about using techniques for federated multitask learning. So in multitask learning, the idea very simply is that you can learn separate models, one for every client in the network, but that you can also learn about the relationships that exist between those models or those clients. So this is a super broad framework. I'm just, providing a very broad instantiation of the objective here, but you can think about, incorporating different, penalties in terms of this regularizer, for example, to learn information about the weights on the edges in a graph where you assume that all of the clients are related. You could learn that there are outliers that exist, that clusters or groups form amongst the network, or maybe that there's some asymmetric relationship. And crucially, what's nice about this is you don't need to know these relationships beforehand. This is something that you can learn directly from the data. So this makes this a very powerful tool for learning over heterogeneous networks. And we've seen this over the last several years. We've looked, specifically at trying to rigorously study the benefits of multitask learning and personalization in federated settings. So this is something that can improve accuracy, but it also has other advantages. It can improve robustness to attack. It can improve fairness of the model across the network, so ensuring a more equitable performance of the model across diverse or heterogeneous networks. And we were quite curious about what the potential advantages or possibly disadvantages of something like multitask learning might be in relation to privacy. And here I just want to note something broadly, which is that privacy is not a binary metric. It can mean many things. And in the context of federated learning, it's important to think about, where sensitive information might be leaked, right? If you're thinking about learning across a set of clients, and developing a model in a federated setting and then deploying that, you might see a workflow that looks sort of like this. There are multiple places where sensitive information could potentially be leaked. You could gain access to the specific clients. You could learn about information being sent over the network. You could gain access to the server, or perhaps, some of the models or metrics that are being developed by an engineer. And another one, which is, I think probably the most common one, is that you can learn information from the model that's actually being deployed, the final model that's learned. And there are various strategies that you can think about for enhancing the privacy and security across various components of this workflow. I've seen that there's going to be some talks, talking about various aspects of this in the context of federated learning. For the talk today, I'm going to focus on this issue of how can we ensure privacy in terms of the final model that we're learning? And this one I think is quite important because this is definitely something that we're going to be giving people access to, right? The whole point is to, learn a model that we can then give access to the clients so they can use that model, right? So this is something that we're going to basically be giving to everyone. And we definitely want to make sure that this doesn't reveal any sensitive information. Okay, so how can we ensure the privacy with respect to this final model that we're developing and deploying in federated settings? A very popular and common technique here is to use differential privacy. I'm not going to go into too many details of this, and I assume that many of you might be familiar with differential privacy, but at a high level, the goal is basically to learn as much as possible about a group, to learn this broad aggregate model while learning as little as possible about any individual in it. So you're trying to, learn a model without learning unique, distinguishing factors about the clients that were used to train that model. Okay. In the context of something like multitask learning, this can actually become sort of challenging, instantiating this notion of differential privacy. And the reason is that if you think about, cross-device federated network, typically what you're trying to do, the metric or granularity of privacy that you care about, is with respect to the individual clients, right? Each of these devices typically represents a client in the network, and we might want to learn a model that, takes into account aggregate information from all of these clients, but doesn't allow us to say, definitively that a particular client and that client's data was used for training. The reason this becomes difficult with respect to multitask learning is that we're also trying to learn models that are personalized to the unique behavior of each of the clients. And what you see with something like traditional differential privacy is that if you naively apply it in conjunction with multitask learning, you get really, really poor performance because you're learning models that are, unique to each of the individual clients, while also trying to ensure that you don't know that that client's data was used to train that personalized model. Okay, so this is a natural tension and an issue with just using traditional DP in the context of something like multitask learning. Okay, what else can we do? What we did in this work is to think about a different, I think very natural relaxation of differential privacy, which is commonly referred to as joint differential privacy. The key idea, which I think is very simple and straightforward, I'm not going to go into the algorithmic definition. Basically, the idea is that we want to ensure that no sensitive information from other clients beyond a specific client is used to, train the personalized model for that client. So we still allow there to be a dependency for, say, user one when developing user one's personalized model on user one's data, but then we have differential privacy in terms of the other clients in the network. So there's this natural sort of decoupling where you can, maintain the, I think, important accuracy that you want to maintain by learning a model that's personalized to each of the users, but you're ensuring that that personalized model doesn't leak information about the other users in the network. Okay. So I'm not going to go into the specific details of, kind of the theory and the algorithmic details here, but I just want to point out some of the key results from doing this. So by using this variation of differential privacy, using this joint differential privacy approach, we were able to get good performance with using multitask learning in a cross-device federated network. And until this point, it was sort of unclear how to actually use multitask learning, which gets this, these great accuracy, robustness, fairness, benefits in practice with differential privacy, which is sort of the gold standard of privacy in federated settings. And we were able to do this with joint differential privacy. And there's two key results here. One is that by doing this, by using this, privacy formulation, we see that our private versions of multitask learning retain sort of the same benefits that you would see in non-private settings, now in private settings. So what I'm showing in this plot is that you see that when multitask learning is useful in a non-private setting, when we then look at instantiating this private version of multitask learning, we get some of the same benefits that we saw in a non-private setting, now in a private setting. What was interesting, though, is that we also saw that it could have additional benefits. So even in scenarios where multitask learning in a non-private setting didn't seem to be super, super helpful, so maybe we weren't in a super heterogeneous environment, we saw that when we moved to a private scenario, so we were training with differential privacy, actually now there were pretty major advantages to using private multitask learning relative to just learning a single model in a private way. So this was really exciting to us, and it encouraged us to dig a little bit deeper and think more about this problem and why we might be seeing these advantages in terms of using private multitask learning and what other applications there may be. And specifically, we looked at how we could apply private multitask learning in cross-silo federated networks as well as in cross-device networks. And an important distinction here arises in cross-silo federated learning in terms of how you think about defining privacy and the granularity of privacy in a cross-silo network. So in particular, in cross-silo settings, you usually don't care about the privacy of the entire client or data silo as much as you do about the individual components of that silo, right? So in a cross-device network, you often think about these clients as being users, and you often care about user level privacy, right? You want to ensure the privacy of each of the users in that very possibly large scale network. In a cross-silo setting, typically, say you're learning over 10 hospitals, typically you know that those hospitals are participating in this procedure, but what you care about is the privacy of the individual patients in those hospitals. So here you typically care less about this notion of client level DP and more about a notion which you can refer to as silo-specific item-level differential privacy. So you care about the privacy of the individual users within each of these silos. So this is important in the context of multitask learning because it changes a little bit how we think about some of these baselines of just learning a local model or just learning a global model. And what you see here actually is that just doing local learning, which in cross-device federated learning is essentially free from a privacy perspective. You're not eating into your privacy budget from doing local training. Here in a cross-silo network, you do start to pay a cost when you do local training. Okay. The ramification of this is basically that what we saw is that in terms of thinking about private multitask learning with this specific notion of silo-specific item-level DP, there were simpler sort of multitask learning baselines that seemed to do really well relative to things that from the cross-device setting we think of as being pretty competitive, things like learning a global model and doing fine-tuning. In the cross-silo setting, this simple fine-tuning baseline, actually you start to pay a big cost for doing this when you're trying to implement this with differential privacy. And what we saw instead is that this simple multitask learning objective, mean regularized multitask learning, this very simply says learn separate models for each silo in your cross-silo network, but make sure they don't deviate too much from the average model. This seems to work actually quite well. This is something that we explored both in theory and in practice, and it has particularly nice sort of privacy utility trade-offs. So this is something, as I mentioned, that we studied. We have a few papers on this topic, but we also went and actually implemented this. And we implemented this. We were excited to see recently this, US UK Privacy Enhancing Technologies Prize Challenge. So this was a broad set of challenges, with roughly $1 million in prize money. And we specifically were looking at trying to, see how useful some of these tools that we had been developing would be for the problem of privacy preserving cross-silo pandemic forecasting. Okay, so the goal here specifically is that you might want to be able to, I think for obvious reasons that we're unfortunately all quite familiar with, be able to predict whether or not, a pandemic or a disease might be spreading across a population. And you might want to be able to do so given access to siloed information, maybe from different hospitals, for example, or different health districts. But crucially, you care a lot about the privacy of the individuals that are sharing this information, right? So you want to be able to do this in a way that maintains that silo-specific item-level differential privacy. Okay, in thinking about a solution for this, we did the following things. So we formulated this as a federated binary classification problem, trying to see how likely a certain individual was to be infected. So what is the likelihood of spread of this disease? Then we used specifically this silo-specific item-level differentially private training. We looked at using model personalization via multitask learning, and we specifically used this approach that we had studied theoretically and shown that it had some key advantages. We used this mean regularized multitask learning approach. And these were sort of the key components. This was a major component in developing this winning solution to the privacy preserving pandemic forecasting. Okay, so let me stop there. I think I'm almost out of time. But the key takeaways from this, the key sort of, punchlines from this work, one is that in the context of federated learning, you have some clear privacy advantages, right? In the sense that you're not sending and sharing all of that data into one central location, but it's still important to think about where sensitive information may be leaked throughout this process. And specifically when you're thinking about differential privacy, which is quite important in the sense that, you want to develop a model that is eventually going to be deployed across these different clients. It's appropriate to, you need to think about how to appropriately define various granularities of differential privacy for the application at hand. So we talked about two specific notions. We talked about differential privacy in cross-device settings through this joint differential privacy approach. And we talked about this silo-specific item-level DP for cross-silo federated learning. Another key takeaway is that multitask learning provides quite significant benefits in private settings. It provides benefits in the sense that if you see that multitask learning is useful in non-private settings, which, we've shown that this is useful not just for improving accuracy, but it has these other advantages as well, that you retain those benefits by thinking about these private multitask learning approaches. But that there are perhaps even some advantages even when you don't see, initial success from multitask learning in a non-private setting. So this is something that I think, is quite interesting to continue exploring in future work. And finally, one of the other takeaways from our work, especially looking at this challenge, is that actually quite simple, highly scalable methods for multitask learning can work quite well in practice. So these are tools that I think are, not too difficult to modify existing solutions from, and are pretty easy to get, implemented and running in realistic federated applications. In terms of future work, we're continuing to explore additional forms of multitask learning, better understand some of these, privacy advantages that we've seen a lot in practice, and develop further general understanding of heterogeneity. We talk a lot about heterogeneity, but I still think we, need better examples of exactly what this looks like in practical federated applications. As one effort towards this, we developed this Motley benchmark recently, which is, trying to get a closer look at federated learning and realistic federated applications. But I think this is continues to be an important ongoing area of work. Great. Thanks. That's all I had. I don't know if I have any time for questions.
So we have time for questions. So any questions from the room? At all? Or online, perhaps? Oh, okay. There's one question on the back there.
Thank you, Virginia, for interesting talk. Actually, I have a question. Are you going to target any kind of standards on the data side in the future?
Oh, so I think the question, sorry, I faded out a little bit at the end there, but the question was, are you going to target what solutions on the data side? Is that right?
Standards regarding data.
Oh, standards regarding data. So by that you mean
For example, in healthcare, we have different standards for managing the data and using the data in the federated settings. For example, OMOP is one of the popular one. So these kind of standards, because they can bring high quality data for federated learning environments.
Yeah, this is a good question. I think that this is something that is really important for the field. In terms of I mentioned this on the previous slide. I think we need better examples of what something like heterogeneity looks like in practice. I think we also need better examples of what these sort of standardizations might look like in practice for different federated data sets. This is something I've been thinking a lot about personally in the context of privacy. So I've been thinking a lot recently about the problem of unlearning, that you might learn a model and then, for various privacy reasons, in terms of the data sets, people might want to delete their data or make modifications to the data on each of the silos. And so you need to think about updating the model that you've learned. I think this is another area where we need a better sense of how people can formally make these requests and what that looks like in practice, and what sort of guarantees we can provide about the final model. But I think going back to the question, one thing I'm quite interested in here in the context of data standards is also thinking about when there might be heterogeneity in terms of the data formatting and standards in a federated network. So this is something that we've been thinking a little bit about, and I think that form of heterogeneity is not often talked about, but might be a real issue in practice.
Great. We have one more question at the front here. I'll just hand over the mic.
Hi, Virginia. Thank you for the talk. It's great things you're doing there. Today, there's been a lot of discussion about the applications of federated learning, and which all seems to be predicated around deploying within organizations that own data. So I wonder, in your research, have you looked at communities rather than organizations? So we know we can talk about communities of practice, communities of interest, communities based on localities. These have their own data, their own outlook, their own concerns about how they want that data to be stewarded, and they want to retain ownership rather than being maybe what we could call strip-mined.
Yeah, I think this is a really important point. One way that we have been thinking about this recently in terms of our research is in developing tools that incentivize people to share data. This is not something that's often talked about, especially in maybe cross-device applications of federated learning, where even though you're trying to improve privacy, you assume that the company owns that data and has access to all of the data. And so you don't necessarily need to incentivize clients to share their data. You assume that you have access to it, right? But in other applications, like applications you're mentioning, we want not only privacy and security guarantees, we want an understanding of, how our data is going to be used and what we're going to get back from that data being used, right? And I think this is a scenario we've looked at, even very simple definitions like If you share your data, you want to make sure that the model that is learned is at least better than if you had ignored everyone else's data and just learned a model on your own local data, right? This should be the bare minimum that we provide in a federated setting, right? You're at least getting something back for, this effort of sharing data. And there's many more complicated instantiations that you can imagine. So this is something that I think is really important for the field moving forward is to think about these incentive mechanisms. And this is something that we have been exploring in our recent work as well.
Great, amazing. So then with that, we're going to go to break. Thank you so much, Virginia, for the talk and the wonderful dialogue afterwards. Thank you so much.